Hi, today I'd like to set up a molecular orbital diagram for the N3- anion in a purely qualitative way to illustrate some of the principles involved with setting up more complicated ideas of bonding and how molecular orbital theory can extend to multi-atom systems. I'm pitching this discussion somewhere in the ballpark of an early stage of a chemistry undergraduate degree course, so I'm assuming some familiarity with the basic principles of molecular orbitals, particularly those being constructed from atomic orbitals, maybe in a diatomic system. And if you'd like to hear more of me talking through some random chemistry topics in a slightly casual style, please do give this video a like and subscribe to the channel if you want to be notified of new videos when they drop. I'm going to jot down some notes about the azide anion. So it is a molecular anion that is linear and is known to be a good nucleophile in organic chemistry, particularly for things like SN2 type reactions. It consists of 3 nitrogen atoms, so one of the first things we need to do here is work out how many electrons are going to be holding our molecule together. So nitrogen has the electron configuration 1s2, 2s2, 2p3. We can group these into 2 types of electrons here. We have the 1s electrons, which are considered core, and what we mean by that is they don't experience very much shielding, so they're feeling the full whack of the 7+ nucleus on the nitrogen atom. So those orbitals are very contracted and are unlikely to overlap with other orbitals to form any sort of bonding type interaction. So we can discount them from the rest of our analysis. These n equals 2 electrons are the valence shell of the nitrogen. So each one of the nitrogen atoms is going to be contributing 5 valence electrons to the bonding. So total number of valence electrons, we can say that there's 3 times 5, which equals 15 from the nitrogens. And we add 1 from the negative charge to give us a total of 16 valence electrons for bonding. Okay, so that's a good start, and we need to think about where they're going to distribute themselves. So we could try and draw a structure for this using a sort of atom and stick type model, or a so-called Lewis structure. So a Lewis structure for this is actually not quite as nice as we might want it to be. If we have a nitrogen bonded to another nitrogen, bonded to another nitrogen in a line, well, we've got to try to get the correct number of bonds to each of these, and the only way we can really do it in any constructive way is to put a positive charge on the middle one and bond it to 4 things, and to have 2 bonds on the outer nitrogens and put negative charges on those. The limitations of the Lewis type approach to drawing certain types of molecules, including this azide anion, these charges aren't really a satisfactory way of explaining how the molecule is held together. So we're going to need to appeal to molecular orbital theory to help us think further about this. So just as a quick recap of what the ideas are in molecular orbital theory, what we tend to do is say you have some atomic orbitals and they're next to each other so that they overlap, that have matching symmetry, size and energy. These atomic orbitals will combine to form molecular orbitals, or MOs, and then we can populate those MOs with electrons to see whether there's an overall net bonding effect for us. So in general, we have to do calculations to help work this out, but in simple cases we can do a bit of a back of the envelope analysis to get us a rough structure, to get us going into our analysis. So if we have, say, 2 atomic orbitals that match symmetry, size and energy, they're going to be slightly different in energy. For example, say I had these 2 different atomic orbitals. When we combine them together, what is generally observed is we'll get a molecular orbital which is higher and one that is lower than the lowest of the original one. So what we're sort of doing here is we get a new molecular orbital that's lower than the lowest original atomic orbital. We call this bonding with respect to the initial orbitals. And we get one that's higher than the original highest atomic orbital, and we call this anti-bonding with respect to the initial orbitals. Okay, and these are our new MOs. It's common to draw these sort of interactions in a slightly different way. So to give an example, e.g. when we've got two s orbitals interacting that are near each other, so we would normally draw this type of thing as, okay, I've got an s orbital over here, it looks a bit like this, s, another s orbital over here. We draw them interacting to form our molecular orbitals, one up, one down, and we'd call these MOs in the middle. This is a sigma bond, and this is a sigma star antibond. The sigma bond will look a bit like this, where electron density is smeared across the whole system, and an antibond will have a node in the middle, and it's higher in energy. Say we had one electron in each of these original orbitals. When we form the new molecular orbitals in the center, we can pair them up and put them both in this lower energy sigma bond, and this decrease in energy represents our bond. Another general result we get from molecular orbital theory that we can still use in a qualitative sense, and that's what happens when we have three atomic orbitals, for example, or any type of orbital for that matter, that have similar size and energy and have the same symmetry to overlap with each other. So say we've got any old three, for example, atomic orbitals. A general result that we have from here, if we were to combine them and to overlap to form molecular orbitals, a general result would be, well, that we would get an antibonding orbital that's higher in energy than any of our previous ones. We would get a molecular orbital that's also lower in energy than the lowest of our original atomic orbitals, and we get a final a molecular orbital that's somewhere in the middle. So the exact placement of this one in energy requires calculations, requires detailed calculations. So we know that we start off with three atomic orbitals and form three molecular orbitals, but we can't really say much about the exact position of that central one. We're going to need to start to combine some of these ideas together. So our job is to try to work out how the electrons can be used to hold the thing together. So we've got three nitrogens in a row, and we know that there's some electron density generally across the whole lot. So we need to have a think about which molecular orbitals we can form from the atomic orbitals from each nitrogen. So just to keep a reminder, we've still got a negative charge on the whole lot here. Okay, having a think about what the orbitals that each nitrogen could contribute to this. Each nitrogen could contribute a 2s, or 3 that each one of these nitrogens is bringing to this molecule. We can start to think about what we might need to overlap. So when each nitrogen here is contributing potentially a 2s orbital, and there's 3 2p orbitals for each one of those. So just to keep the distinction, we're going to have a px, 2py, and a 2pz. So each one of those orbitals is at right angles to each other. So we've got 4 atomic orbitals from each one, and there's going to be 4 atomic orbitals from this one, and 4 atomic orbitals from this one. So we're starting to get into quite a complicated problem. So altogether there are 12 atomic orbitals in total. So our original models, where we've got down the bottom here, where we've got a combination of 2 molecular orbitals, 2 atomic orbitals to form 2 molecular orbitals, is something that we can do qualitatively. But also combining 3 together, we can make 3 molecular orbitals with a bit of uncertainty about the energy levels of the central molecular orbital there. How do we deal with a problem like this? And the answer is we need to appeal to the symmetry of the situation. So having a look at our nitrogen structure, we can sort of quite quickly tell that there's a there are two types of nitrogen in this molecule. There's this central one, which I'll label as nitrogen type 1, and there are these two on the outside, nitrogen type 2. But by symmetry, the terminal nitrogens are equivalent. So to help us deal with the large collection of atomic orbitals that could be overlapping here, what we can do is define so-called symmetry orbitals. And for reference, these are often called different things in different contexts. These are the same idea as ligand group orbitals, which often occur in analysis of transition metal complexes, or also symmetry-adapted linear combination, or SALCs. These are all the same sorts of idea here that we're going to talk about. So on atom 2, for example, I can take the two s orbitals from the two nitrogens and define a symmetry orbital of this one, and on the final one, another in-phase s orbital. So these are not overlapping, they're not a molecular orbital. And what I'm going to do going forwards is treat this whole unit as one symmetry orbital and see how that can combine with the nitrogen atom 1's orbitals. I can define another symmetry orbital as the outer phase combination of these two s orbitals, something like this. Again, not overlapping, just grouping them together so that I can overlap them in a clear way with nitrogen atom 1. With the p orbitals, so say a p orbital on this left-hand one can form a group with this one on the right-hand side. This can form a symmetry orbital of those p orbitals, and we can define that in phase or out of phase in exactly the same way. So there's two more symmetry orbitals, that's the central atom, and that's another group symmetry orbital. So there's a few more p orbitals to deal with on those nitrogens. In particular, there's some that point along the internuclear axis along the line of the molecule. So a p orbital that does that, for example, might look like this. It's a central atom, and then in phase with another p orbital on the other end. There will also be an outer phase combination that will look something like this. And these are two new symmetry orbitals. Finally, there are a couple that point in and out of the plane of the paper. So we're going to group those two together, one on each end, in phase, and again define a final symmetry orbital as the outer phase combination. So that's two more, and in total we'll have 8 symmetry orbitals based on nitrogen atom 2. Well, now we can look at these symmetry orbitals and see how they combine as a group instead of individually with nitrogen atom 1. So just to keep a track on what type of orbitals nitrogen atom 1 has, it's got a 2s orbital, it's got a 2px, a 2py, and a 2pz. And they'll interact differently with these different symmetry orbitals. So if we work out all of the types of overlaps we've got, we'll be able to construct our molecular orbital diagram quite quickly. So to start with, we could take, say, the 2s orbital from nitrogen atom 1, and we can see that that interacts quite nicely with our symmetry orbital in the top right. So slotting into here, this would be certainly one way that we could form a bonding type orbital. And we can form a bonding or an anti-bonding combination using that 2s in here. We can see from that second one on the left that maybe we could use one of the p orbitals, the one that points specifically along the internuclear axis. That's normally defined as the pz one. So 2pz. That will overlap nicely there to form a bonding or an anti-bonding combination of molecular orbitals. So where this might get a little bit tricky is that if we have a look on the right-hand side now, there is actually another orbital that can combine with the 2s, which is this one here. And indeed, there's another one that can combine with the 2pz, which is up here. So we're going to need to factor in that our 2s orbital, for example, just to put a star by it here, can combine both with this symmetry orbital and with this one. But that's okay because we have a method for dealing with three orbitals interacting with each other. It means we don't have enough information to determine the exact energy placement of the central molecular orbital. We're going to get three molecular orbitals from our three atomic orbitals, but we can say something about the highest and the lowest, and that's all we're really going to need to go forwards with this. Okay, if we have a look at the bottom symmetry orbitals in our list now and see what they can combine with. For example, there's a remaining p orbital here that can combine to form in-phase and anti-phase combinations with this symmetry orbital, so the third one down on the left, and the third one down on the right can do a similar thing with the outer plane one there. So the interesting part comes with what do we do with these bottom symmetry orbitals? Well, there is no orbital that N1 is presenting to us that can fit in here, and there's nothing here. So these symmetry orbitals can't interact with anything on the central atom. Okay, we're now at a point where we can consider putting this all together as one big molecular orbital diagram. So to start with, I've put my nitrogen atom of type 1, that's the central nitrogen here on the left-hand side, and that's got its two s orbitals and its two p orbitals. Now to represent the symmetry orbitals for the N2 type atom, we're going to need to draw them in. As we might recall from the diagram before, there was no overlap, these were just groups of atoms, so we'd expect their energies to be roughly the same as the unmixed or uncombined p orbitals and s orbitals involved with nitrogen. Although if we have a look, some of the combinations, some of the symmetry orbitals were in phase and some of them weren't, so maybe there is a slight difference, but it's not going to be major. Orbitals related to the 2s orbitals on nitrogen number 2 type. We've now got all of our symmetry orbitals accounted for, so that's 8 orbitals on the right hand side. So what we're sort of saying is that this gap indicated here is pretty small for both the 2s and the 2p symmetry orbitals, but we're acknowledging that there is at least some type of overlap between them. So for example, this orbital here, where you've got two in-phase ones, even though they're far apart, there will be some overlap. We're going to say that that's ever so slightly more stable than this one here, where there's an anti-bonding interaction between equivalent orbitals. The orbitals that are on the left-hand side for the type 1 nitrogen, and we can start to combine these together. So we identified before that the 2s orbital here with a red star, we saw that that interacted with both this symmetry orbital in red, so I'll just put a red box around these ones. There'll be an interaction between those two, which have a similar energy, so that'll be a really good interaction. But there's also another orbital up here that these ones can interact with. So there's 3 molecular orbitals there in red boxes that we have to combine. So we know that the lowest energy orbital will be lower than any of the other ones. So the lowest ones we have here are the 2s or the 2s symmetry orbital themselves. So we'd expect the lowest bonding type orbital to be somewhere down here. That's the in-phase combination of those. There should be an anti-bonding one, which is higher in energy than the highest one with a red box. So for example, I might be able to put that somewhere like here. And we know that there's another orbital somewhere in between those, because three components coming together to form 3 molecular orbitals means there must be one. We could put it slightly in the middle, but we do know that there are 2 of the orbitals in red boxes that are quite low down here, so maybe I'm going to weight it slightly and put the remaining orbital somewhere around here and just sort of say that the position is uncertain. Okay, the next thing we could do is look for those other sets of orbitals that combined, and there was another set that was that there were 3 that have the correct symmetry to overlap. So that's this one down here in green, the symmetry orbital coming from the out of phase grouping of the 1s orbitals. That can interact with this p orbital here, and it can also interact quite nicely with this one here. So again, we can do the same sort of deal where we should have one going up, one going down, and one somewhere in the middle. We can also acknowledge this time that there are two near the top, like this one here and this one here, that are both coming from the P parts of this. So maybe the interaction should be biased towards those ones, by which I mean maybe the interaction is strongest between those top two, and that would send my antibonding orbital the highest up there. As a counterpoint to that, the S component of this is less important in that combination because it's only 1/3 of the set. So maybe that one doesn't go down as far as this one, but there will still be one more bonding orbital underneath the energy of this orbital here. There'll be another one somewhere in the middle. Maybe it's slightly more towards the p orbitals for the same sort of reason. So I'm just going to put that in somewhere like here and say that the position is uncertain. So we formed from the green boxes, we formed 3 molecular orbitals in the central diagram. So that leaves us with a few more to go with. So we have a p orbital here in the purple box, and there's only one orbital with the correct symmetry for that one to overlap with, and that's this one here. So that will form a molecular orbital, an anti-bonding and the bonding combination. If we look a bit more carefully, there's actually a second one that's very similar. If we have a look at this one, I'll put a double purple box around this one. We'll do a very, very similar thing. In fact, it will be exactly the same energy as the interaction of the double purple box with this one. So we'll form a degenerate set of pi bonded MOs. A pair of them will be bonding, so it's only a pi interaction, so it's not as strong as any of the sigma ones that we've drawn to this point. And there'll be a set of anti-bonding ones as well. So these ones are anti-bonding pi type, and this is bonding pi type. Finally, we can see that there's actually a couple of orbitals that we haven't used at all here. So just highlighted in yellow, we've got this one that's got nothing of the correct symmetry, and this one as well. These ones don't do anything in our diagram, so I'm just going to carry them across. They will end up being non-bonding orbitals and will just stay at the same energy that they were before. Obviously, it's not perfect. There are some bits we'd need to tidy up. We'd need to do some calculations to determine the ordering. So calculations required to determine the exact ordering of those ones. And also there is some ambiguity of exactly how strong this pi interaction is in the middle relative to some of the sigma interactions. So now the next job will be to fill us up with electrons. So we've got 16 valence electrons that we determined at the start. So filling them up from the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So actually the ordering of some of these orbitals to some extent isn't important. Things that we could do with this if we wanted to would be to predict some of the reactivity. So for example, these would be our highest energy electrons, they would be our highest occupied molecular orbital. They're in fact non-bonding orbitals, or we could maybe define them as lone pairs. If we have a look at the yellow highlighted orbitals, we see that all of our electron density is on the terminal nitrogens, which kind of makes sense because in our Lewis structure before, we had 2 negative charges on the outside. So this was our structure beforehand. And this is in line with the fact that there's a lot of electron density on the terminal nitrogens. Our lowest unoccupied orbital will be one of those anti-bonding pi orbitals, or pi star even, in the middle. So if we were to need to know about the lowest unoccupied orbital, we've also got a handle on what that would be as well. Although bearing in mind that this is the N3 anion overall, the highest occupied orbital is the most important to us to determine this molecule's reactivity. I'd just like to point out how the shapes of these orbitals that we've combined together might look. Just before I do that though, when I recorded the previous bit, I realized that I joined up some lines incorrectly. So on the molecular orbital diagram here, these green lines should be connecting just the green highlighted orbitals. So to have a look at the shapes of the combined molecular orbitals, I just want to take the red ones for now. So that's this one over here, this one over here, and this third one up here, and have a think about how we might think about the shape of them. So these are the red highlighted orbitals just here, and how we might combine them. We've seen from our molecular orbital diagram that these guys are coming from the 2s. So these are the most similar in energy. Most similar in energy. So forming, say, the fully bonding combination of these, we might expect them to contribute more because the final molecular orbital is closer in energy than those ones. This symmetry orbital has come from 2p's, so maybe it should contribute less to the overall system. So a first shot at sketching what this molecular orbital should look like, well, we've got 3 atoms to think about, and we can see that the first 2 orbitals are going to give us lots of electron density just generally on the nitrogens, which is fine, and the final orbital is just going to cancel out some of the wave function just in these outside of the molecule regions over here. So maybe the final overall molecular orbital looks generally like there's quite a lot of electron density just generally in the middle and not so much just outside, which sort of makes sense for a really bonding MO overall. Okay then, I hope you enjoyed this video. If you want to go further with this type of approach, you really should be trying to formalize some of the approaches taken here using the language of group theory. But in the meantime, if you liked what you saw, please give this video a like, and if you want to see more content along this sort of style, please subscribe to my channel and let me know what type of things you'd like me to talk about.